Okay, so today we're doing a midterm review. So we're going to go over all the things that you don't feel you have quite mastered yet. And this is for General Chem 1. All right, so shout out some of the things that you'd like to spend time today talking about, and we will go over those things. Yes?
First question is for the electronegativity chart. Is that supplied for the test?
No. You need to know electronegativity rules. So let's just put some rules on there, because there are some patterns you can follow. Electronegativity rules. Okay. What are some other things you want to talk about? You guys made lists of things you want to talk about. So what are some things on your list?
Molecular geometry.
Molecular geometry, okay.
And electron.
Molecular geometry. That's Vesper. Okay. And what else?
Net ionic equation.
Net ionic equation. Okay.
Do the construction of like the Lewis structures, which lead to all into that.
Okay, so molecular geometry and Vesper / Lewis as well.
Yes.
Okay. What else? That's probably all we're going to be able to get to today. But let's go ahead and make our list so I can see how big of a bite we need to take.
Intermolecular forces.
IMFs, okay. That goes along with Vesper.
Empirical formulas.
Empirical formulas, okay.
Identifying acids and how they go with weight.
Identifying acids. Was that on Mastering Chem somewhere?
There was stuff about acids.
We don't do any acid base in Chem 1. That's in Chem 2.
It was in the book.
It was in the book, but we don't cover those sections in Chem 1. We save all our acid base for Chem 2. Anything else? Those are some big topics, so we'll get to as many as we can today. Is there anything else we want to put on the list, though? We can get to it on Friday if we can't finish it today. Yeah.
How to like identify your polar, non-polar, especially like science.
Okay, so that goes along with this polar, non-polar. Oh, polar and non-polar solvents.
And science.
That still goes on with IMFs.
Okay.
Polarity. Yep, that goes along with IMFs. I saw another hand up. Yeah.
Of how to correctly create an equation. Because like I know how to get certain things, but like I know how to balance it once I get it to.
But predicting the products.
Yeah, predicting.
Okay. Predicting products. Okay. I saw another hand up somewhere. Yes. Stoichiometry. Okay. Anything else? Yes. Solution stoichiometry. Okay. We'll definitely be getting into this on Friday because we're not going to cover all this today. That's okay. That's okay. I wanted to have a nice big long list so that we have everything ready. So part 1, we'll get through as many today as we can, and then we'll do the rest on Friday. So I think we can do electronegativity rules right now because that one's quick. On your periodic table, and mine's actually labeled because I went over this in my last class too. Your most electronegative element is fluorine. Most electronegative element is fluorine, so label that on your periodic table somewhere. Most electronegative elements fluorine, and electronegativity increases going across a period, so it increases going across a period. So that means fluorine's more electronegative than oxygen, oxygen's more electronegative than nitrogen, nitrogen's more than carbon, carbon's more than boron, etc. Right? It increases going across a period, it decreases going down a group. So fluorine's more than chlorine, chlorine's more than bromine, bromine's more than iodine, etc., etc. Right? So it increases going this way, it decreases going this way. So if you are choosing between, say, chlorine and iodine, who's more electronegative? Chlorine, right? If you're choosing between sulfur and magnesium, who's more electronegative? Sulfur, okay? Now for if I'm asking you to calculate the electronegativity difference, is that what you're talking about? I would give you those actual values. I'm not going to make you memorize actual values, but I would expect you to be able to predict who's more electronegative just based off their position on the periodic table. Okay? So if I asked you what's the bond polarity of a beryllium boron bond, I'd have to give you those values. But I could say who's more electronegative, and you look at the periodic table and figure it out. Okay? Does that sound good? So that one's easy. We can cross that one off the list. So for today, let's focus on, because these all kind of go together. Let's do this guy, and this guy today. Okay, we're going to do the Vesper IMF's polarity today. I think we can probably do all that in an hour. And then we'll do everything else on Friday. Let's see, these guys go together, and then that's kind of a standard thing. So we'll focus on these three today. If we get to any extras today, awesome. But let's focus on those for today. So we're going to do Lewis. I'm just making a note to myself. Vesper. And then molecular geometry and IMFs / polarity, because that all goes together. Now I will tell you that the Vesper chart is going to be given to you on exam 2 as a reference page. You're not going to have to memorize the Vesper chart, but everything. Oh. That was for myself. But for everything else, you need to be able to replicate that on your own. Okay, so let's get into Lewis structures first. So here are the rules for Lewis structures. Now let's talk about, before we even go any further, what's the difference between Lewis structures and Vesper? Just out of comparison versus Vesper. Vesper stands for valence shell electron pair repulsion theory. Okay? Vesper shows you the 3D shape. Okay, Vesper shows you the three-dimensional shape, whereas a Lewis structure is planar, right? Mash those two words together. It's flat. It's like a photograph versus a sculpture. Okay, if you take a picture of somebody, that is a planar representation of that person. You can't tell any depth. Versus a sculpture of that person, that's a three-dimensional representation. So 3D printer versus taking a picture, right? So Lewis structures are flat. They give you a general idea of the shape, but they don't get into the specifics. Whereas Vesper theory shows you the actual three-dimensional shape, and that's really important to us as chemists, because how a molecule is shaped determines how it reacts, especially if you start working at organic chemistry, which I hope you pursue chemistry further and you take organic, right? You're really going to be interested in three-dimensional shapes. So Lewis structures are flat. They're like a photograph. They're nice. They give you a good general idea. But until you actually look at the three-dimensional shape, you really don't get a good idea of what it's going to look like. Okay, so that's the difference conceptually between the two. So let's talk about how we do a Lewis structure and then how we turn Lewis structure into Vesper. So the first thing we need to do is you need to calculate the number of valence electrons. Okay, and that's from the periodic table. Use the periodic table to do that. Then you're going to pick the least electronegative element and put it in the center. Okay, we just talked about electronegativity, right, 5 seconds ago. So the least electronegative element goes in the middle, right? Because electronegativity is a measure of how well you share. If you are not good at sharing electrons, you don't need to be put in a position where you have to share, right? Because electronegative elements don't share electrons that they're in bonds with very well. They're lousy at sharing, right? So, for instance, if you're thinking about it in terms of people, right? I have a 2-year-old. He's very electronegative when it comes to toys. He doesn't want to share, right? So let's not put him in a position where he has to share. If you are highly electronegative, never put that element in the middle. Pick the least electronegative because it's good at sharing. Put someone who's good at sharing in a position where they have to share. Okay. Connect remaining atoms with single bonds. All right. And then give outer atoms an octet. Octet means how many electrons? 8, right? And a single bond is worth how many electrons? 2, right? So octet means they need to see 8 electrons. Now there are some exceptions. Hydrogen, beryllium, and boron are the 3 exceptions that you need to commit to memory. Hydrogen only needs 2 valence electrons, beryllium only needs 4, and boron only needs 6. Okay? And the reason for that is a formal charge answer. If you'd like the long answer, we'll spend extra time talking about why. Otherwise, you can just commit it to memory. The reason why is if beryllium and boron have more, it makes your formal charge a train wreck. So 4, 6, and hydrogen's 2. Okay, give your outer atoms an octet. Step 5, extra electrons go on central atom. Okay, and then 6, if necessary, make double/triple bonds to give central atom an octet. And then if you do step 6, you need to, that's an optional one, right? If necessary. And then step 7, if necessary, if resonance exists, use formal charge to pick the best resonance structure. I know if I'm writing down low like that, it's kind of hard for you to see, so if you need to move. My webcam only picks up in this range right here. So unless I'm like constantly turning the camera, I can't really record. So those are the rules. These are the same rules that are posted in the notes online, just kind of summarized. So calculate valence electrons, pick the least electronegative atom, put it in the center, connect your atoms with single bonds, give the outer atoms an octet. Extras go on the central atom, make double or triple bonds only if necessary to give the central atom an octet. If there's resonance, use formal charge to pick the best resonance structure. So we're going to go through examples, 2 or 3 of these. And I think while we're doing Lewis structures, we'll go ahead and do Vesper at the same time. I think that makes more sense. So let me pause the recording here while I fish out our Vesper hand. Okay, so we've got our Vesper page ready to go here for when the time comes. So let's go through some examples. Is everyone okay if I erase the rules so that I can stay in the screen where my camera will pick me up? All right, so let's go through some examples. We're going to start with a couple easier ones, and then we'll work our way up. And we can actually figure out if they're polar and nonpolar all at the same time, too. So we're just going to do all of this at once. Okay, we're fine. All right, let's do 3 at once. This was actually one of the ones that was in the lecture, but it's a really good example. So let's compare. Let's do methane, CH4, water, H2O, and ammonia, NH3. All right, so we're going to do Lewis structures for all these guys. We're going to figure out their molecular geometry for all these guys. We're going to decide if they're polar or nonpolar for all these guys, because they're 3 great examples that I think will really help just kind of bang it all out. So first of all, let's do the number of valence electrons. So you need your periodic table. If you don't remember how to get valence electrons from the periodic table, write this on your page. Like I said, this was the same stuff I went over last period too. Everybody in group 1's got 1 valence electron. Everybody in group 2's got 2 valence electrons. We skip the transition metals because they vary. Everybody in group 3's got 3 valence electrons, 4, 5, 6, 7, and 8. Okay, so to get the number of valence electrons, it comes directly from the periodic table. The periodic table I'll give you on test is just this same one, it's just blank. So you'll need to commit to memory how to obtain the number of valence electrons. It comes from the periodic table. Okay, so for methane, number of valence electrons. Carbon has how many valence electrons? Look at the periodic table. 4, right? And there's 1 carbon in this molecule, so that's 4. And hydrogen has how many? 1, it's in group 1, and there are 4 of them here. So that's 4, so my total number is 8. Okay, now let's pick the central atom. Hydrogen can never, ever, 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 ever be the central atom. Why? It can only form how many bonds? 1. It can only form 1 bond, right? So it would make it doesn't make sense to put it in the middle because it can only form 1 bond. So by default, carbon's got to be the central atom, right? So carbon goes in the middle. Connect all the other ones with single bonds. 2, 4, 6, 8. So I've used up all 8, right? So I've got no more electrons left. Now I evaluate my structure. Does everybody have an octet? Who needs one? Does hydrogen need an octet? Does it need 8 electrons? No. So happy, 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 happy. Does carbon have an octet? 2, 4, 6, 8. Yes, it does. So that is my final Lewis structure. I'm just going to clean up here. That's my final Lewis structure. No resonance, no double bonds. It's really simple. All right, so let's figure out the molecular geometry for methane. Pull out my Vesper chart. Okay, so what you want to do is you want to count the number of things on the central atom. So each thing attached to the central atom is called an electron domain. All right, so how many electron domains are on the central atom? You've got 1, 2, 3, 4, right? 4 bonds, right? So obviously this one's out, this one's out. We got to keep looking until we find one that's got 4 electron domains. Hey, there it is. Okay, so this is called the electron domain geometry, and this is called the molecular geometry. So the difference between electron domain geometry and molecular geometry is electron domain geometry just looks at the number of things on the central atom, whereas molecular geometry looks at the number of things but subtracts out the number of lone pairs. So in other words, are there any lone pairs of electrons on the central atom here? No. So that means the electron domain geometry and the molecular geometry are going to be the same. The electron domain geometry for this molecule is tetrahedral because there are 4 electron domains. And because there are no lone pairs, the molecular geometry is tetrahedral. So the molecular geometry, the EDG is tetrahedral. And the molecular geometry is also tetrahedral. So if you're looking at this in 3D space, you've got 1 hydrogen coming out of the board towards you. You've got 1 of these hydrogens behind the board, okay? And then these 2 hydrogens are in the plane of the board, okay? So 1 coming out towards you, 1 going behind you, and then 1 in this plane, and then 1 in this plane, okay? So it extends into this plane, and behind, and then there's this plane. Okay, so that's what this molecule looks like. Tetrahedral electron domain geometry, tetrahedral molecular geometry. They're the same because there are no lone pairs. Is everybody cool on how we did methane, CH4? All right. Now, let's ask ourselves, is this a polar molecule or not? So polarity, I'm going to get this out of the way, clean up our space. Polarity asks the question, are there areas of the molecule where there's a positive region and a negative region? Is there high electron density on one part of the molecule that there isn't on the other molecule? So, are there any lone pairs on this molecule? No. If there are no lone pairs, you're at a good chance of it being nonpolar. There's a good chance of that, but always double check. All of these bonds are carbon-hydrogen bonds, right? So the electronegativity of carbon is virtually the same as the electronegativity of hydrogen. If you look it up in your chart, I think carbon's 2.4 and hydrogen's 2.1, I'm pretty sure. So the electronegativity difference here is 0.3, it's like 0.3 or 0.4. So it's nonpolar. If this is a nonpolar bond, and this is a nonpolar bond, and this is a nonpolar, they're all nonpolar bonds, could this molecule ever be polar? No, right? Because there's no area of the molecule where you're like, wow, I've got a lot of electron density. So this molecule is also classified as nonpolar. Now, just a reminder that this is not necessarily related to this. It can be, but not always. You also have to look at the bonds themselves. Are there lone pairs? And is there a bond that's like way, 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 way polar and is being offset by something else? So we'll go through a couple other examples, and I hope that it clears things up a little bit. We're going to do these three plus one more, and I think we'll be crystal clear after that. Everybody good on methane? Nonpolar molecule, tetrahedral, in both electron domain and molecular geometry. All right, let's do water next. We got to calculate number of valence electrons. Hydrogen still has 1, right? And there are 2 hydrogens in the molecule, so that gives me 2. Oxygen has how many? 6. And there's 1, so that gives me 6 for a grand total of 8. Okay, who goes in the middle? Again, it can't be hydrogen. That's nonsense, right? So oxygen goes in the middle. Let's connect with single bonds. So 2, 4. So I've got 4 left over. Do I need to give these hydrogens an octet? No, because hydrogen's an exception to the octet rule. So where do these 4 go? I've got 4 left over. I can't put them on hydrogen. That's not possible. So where do I put them? On the central atom, right? So 1, 2, 3, 4. Now let's evaluate my structure. Does hydrogen need an octet? No. Does hydrogen need an octet? No. Does oxygen have an octet? Yes. 2, 4, 6, 8. All right, so this is complete. That's what the Lewis structure looks like. However, this is not a good representation of the three-dimensional shape because in space, these electrons and these electrons are highly repulsed by each other. Highly, highly, highly repulsed by each other, right? 2 negatives, they don't want anything to do with each other. They're going to, this molecule is going to configure itself so that these electron densities are as far away from each other as possible, right? So when you look at the three-dimensional shape of this molecule, it's not going to look anything like this Lewis structure. So let's pull out our chart and figure out what the three-dimensional shape of this molecule is. All right, so how many things are on the central atom? Ooh, be careful. 4, right? There are 4 things on the central atom. There's this bond, and this bond, and this lone pair, and this lone pair. Lone pairs count as electron domains because they're electrons, right? So there are 4 things on the central atom. So again, we got to go back to the tetrahedral. So I just kind of goofed up my Lewis structure. And it's actually better that I draw it up here anyway. All right, there are 4 electron domains, right? 2 lone pairs and 2 bonds. So the electron domain geometry is tetrahedral. But the molecular geometry is not tetrahedral, right? It can't be tetrahedral because it's only got 2 bonds. 2 bonds, 2 lone pairs. So which one of these is it? It's bent, right? It's bent. So what does that mean? Again, these two lone pairs want to be as far away from each other as possible. So, right, this one is in the plane of the board, this one's in the plane of the board, this one's coming out of the board, that one's going behind the board. So it would look like that, right? So the molecular geometry, this is not a good representation of what it really looks like, right? Because in reality, it's bent. You want to, these two lone pairs grossly affect the 3D shape of the molecule. Okay, so it's very, very different from what this Lewis structure represents. Does everyone see why the molecular geometry here is bent? Tetrahedral electron domain, because there are four things, but molecular geometry is bent. Now let's ask ourselves, is this polar or is this nonpolar? And again, sometimes it's more helpful to look at the Lewis structure, sometimes it's more helpful to look at the 3D shape. So if we're looking at the 3D shape, those take up a lot of space. Okay, is there a region of this molecule where there's high electron density? Yes, there is. When we draw what's called electron density maps, okay, where you color in the density, red is high electron density, blue is low electron density. So if we were to color this in, color code this, we would color this region right here like screaming firehouse red, okay? Because there's high electron density here, right? Because this is a polar bond, which means oxygen's hogging all the electrons and hydrogen's left out in the cold. This is a polar bond, which means oxygen's hogging these electrons. Plus there's a lone pair and a second lone pair, right? This is just like burning on fire with bright, bright red. And this would be like blue, hypothermia blue, right? So this is a very polar molecule. Very, 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 very polar molecule. Very polar. While we're at it, let's do our IMFs. Oh no, let's not. I'd love to do it, but I don't think we can do that in 5 minutes. We'll try. I'll leave this stuff on the board and then we can try to fit IMFs in.
So we tell polarity by doing the molecular geometry.
Yes, and combining that with what you know about the bond polarity too. Because this is an extremely polar bond, this is an extremely polar bond. Plus we've got these two lone pairs just parked here on the central atom. So yes, you have to combine them both together. Yep. Does everyone see where we got the fact that this is a polar molecule? Extremely polar. And you might have even learned this in your biology classes about water being a polar molecule. Yes. We represent this with an arrow that looks like this. Right? So it points towards the direction of the positive and the negative. So here, water is so screamingly polar that when you draw it, here's what the shape will look like without my lone pairs on it. It's got two of those dipole moments, right? So this is the partial negative region, this is the partial positive region. It's got two partial positives and one partial negative. Do you remember seeing that when you were watching the lectures originally? You can calculate dipole moment, it's a measure of polarity, and the dipole moment value for water is really high because water is really, really polar. Think one of my cheesy little bumper stickers. Yes, dipoles have a moment, do you? Right? Dipole moment's a measure of how polar a molecule is. So you can calculate dipole moment, I'm not going to make you, but that's a measure of how polar the molecule is. And water is a really, really polar molecule. Okay, let's move on to, if everyone's ready, are we ready to go on to ammonia, NH3? Okay, so let's do NH3. Calculating number of valence electrons first. You've got to do that before you can do anything. Periodic table. Nitrogen is how many valence electrons? 5. So that contributes 5 because there's only one nitrogen. Hydrogen is how many? Still 1. And there's 3. Just adding them already. So that gives me 8. Again, hydrogen can't be in the center. There's no way it can be. So nitrogen's got to be in the middle. Connect with single bonds. 2, 4, 6. Got 2 left over. Do any of these hydrogens need an octet? Nope, they sure don't. So what do I do with those 2 electrons? Throw them on the middle. Does nitrogen have an octet? Do I need to make any double bonds? Could you ever have a nitrogen-hydrogen double bond in the first place? No, that's not possible, right? Because hydrogen only needs 2 valence electrons. So a double bond involving hydrogen wouldn't exist anymore. All right, so there's my Lewis structure. Now let's pull our chart back out. How many domains does this molecule have? 4, good. So the tetrahedral is the electron domain geometry. E, D, G, tetrahedral. But what is the molecular geometry? I'm kind of writing on top of it. Trigonal pyramidal, right. So this lone pair up here on the top takes up all this space and it kind of depresses all these bond angles. It smooshes them down. So you've got one in the board, one coming out of the board, one going behind the board. So this is trigonal pyramidal. Does everyone see how we got that answer? Just reading it off the chart. This chart I'll give you as a reference page on tests. I'm not going to make you memorize. Okay, I mean, you want to, great, but it's not going to be something I'm going to make you memorize. All right, let's smoosh this down so we can clean up our space here. Now let's ask ourselves, is this polar or not? Is a nitrogen-hydrogen bond polar? Yes, it is. And there are 3 of them. However, you might say, well, this one offsets this one, and this one offsets this one, and this one offsets this one. And that is true. But what do we have here? A lone pair. And is this lone pair being offset by anything? Is there anything on the other side of the molecule that would offset it? No. So you got this big electron density right here on the nitrogen, and therefore, would this be a polar molecule? Yes, it is polar. Is it as polar as water? Not as polar as water. But it is still pretty polar. Don't get me wrong. The dipole moment for ammonia is not anything to sneeze at. It's not as bad as water's, but it's still pretty polar. All right, so if we were drawing our dipole moment, we would draw it this direction, towards the nitrogen. And actually, we would draw it in 3D space. You know, you've got this one going behind the board, this one coming out of the board, this one in the board, there's nitrogen. Right, you draw it towards the nitrogen. Okay, so that's a polar molecule as well. Does everyone understand how we diagnosed the molecular geometry and then we decided whether or not it's polar? Does that make sense? Okay, I've got one more example that I want to show you. It kind of ties Lewis structures and formal charge together, and then we'll get into a little bit of IMS if we have time. I think we can. So let's do carbon dioxide, because this is a great example to talk about for a Lewis structure standpoint, from a Vesper standpoint, and from a formal charge standpoint. We can do all of them at once. Okay, so number of valence electrons. Carbon has how many? 4, and there's 1, so that's 4. Oxygen has how many? 6, and there are 2. So we've got 16 total. Who goes in the middle and why? Carbon goes in the middle, and when I ask students to tell me why, a lot of students tell me, so it could be symmetric. That's not the reason. Why is carbon in the middle? It's the least electronegative, right? So carbon goes in the middle, C, connect with single bonds, 2, 4. So we've got 12 left to go. What do we do next? Give the outer atoms an octet, right? So 2, 4, 6, 8, 10, 12. Okay, I'm out of electrons. I can't just start adding any more, right? Once I've used up my 12, I'm done. So now we evaluate our structure and ask, do we have octets for everybody? Who needs one? Oxygen's got 2, 4, 6, 8. This oxygen's got 2, 4, 6, 8. How many does carbon have? 2, 4, right? So does this carbon have an octet? No. What do I need to do in order to give it an octet? We can form double bonds. What's one solution?
2 double bonds.
We can make 2 double bonds, right? So you can take this one here, make a double bond, And then we could take this one on this side, right, make a double bond. That's one solution. What's another solution? Right, we could do that, right? Wouldn't that work as well? Would that still give oxygen an octet and carbon an octet? Yes, so when you've got two possible Lewis structures, that's called resonance. And you use formal charge to pick the best. Because one of these is the correct answer that I would accept as the right answer on a test. And the other one, I would say, -1, you picked the wrong resonance structure. Okay? So what is formal charge? It's a calculation that we do to show the relationship between the position of electrons and how it affects the molecule as a whole. So formal charge is equal to valence electrons minus 1/2 of the bonding electrons minus the paired electrons. So valence minus 1/2 of bonding minus paired. So in other words, these are your lone pairs. And these are your electrons in bonds. Okay, so let's calculate the formal charge for each atom. Now the goal is all formal charges equal 0. And if that's not possible, have a negative formal charge on an electronegative element. So if you can't have all your formal charges be 0, the next best thing is to have all your negative formal charge on the most electronegative atom, whatever that is. So let's calculate the formal charge. Let's start here. So valence electrons. How many valence electrons does oxygen have? Oxygen, the atom, oxygen has 6. Okay, how many bonding electrons does it have? 2, 4, right? So minus 1/2 of 4. Minus, how many paired electrons does it have? 1, 2, 3, 4. So that's 6 minus 2 minus 4, so that gives us 0. Is this one's formal charge going to be exactly the same? Yes, because it's got 2 lone pairs, and 2 lone pairs, and 2 double bonds, and 1 double bond. Now we just got to calculate this one. How many valence electrons does carbon have? 4. How many bonding electrons does it have? 2, 4, 6, 8, right? So 1/2 of 8. How many lone pairs does it have? 0. So that would be 4 minus 4 minus 0, so that's 0. So for this guy, 0, 0, 0. Well, that's what we want. But let's prove to ourselves why this one gets rejected. The way we know that this one gets rejected is by formal charge. All right, so for formal charge here, oxygen has 6 valence electrons, right? Minus 1/2 of, how many electrons is this? 2. Minus 2, 4, 6. So that's 6 minus 1 minus 6. So that gives me -1. All right, let's do this carbon. Carbon's got 4 valence electrons, minus 1/2 of 2, 4, 6, 8, right? How many lone pairs does it have? 0, right? So this is still 4 minus 4 minus 0, so that's 0. And then for this one right here, 6 minus 1/2 of 2, 4, 6. minus 2, right? So that's 6 minus 3 minus 2, so that's a positive 1. Now you know you did your you know you did your formal charges correctly if they all add up to the total charge on the molecule. This is a neutral molecule, right? This plus this plus this adds up to 0. So I know I did my formal charge correctly because they all add up to 0. This all adds up to 0. So now I just got to pick the best one. Which is the correct Lewis structure? Left or right? This one, right? And if I said, why is this the correct answer? You would say because all the formal charges are 0. Right? That's the best Lewis structure based on formal charge. Now let's go figure out what the molecular geometry of this molecule is. But before I do that, does anyone have any questions on how we did the formal charge calculation? No? Okay. So now, are you okay if I erase this? Okay if I erase this? Let's clean up our mess here a little bit. And let's figure out the VSEPR part of this. Because we're only going to do VSEPR for the best Lewis structure. There's no need in wasting our time on doing it for something that isn't the best Lewis structure. So here's our Lewis structure. And now let's look at our VSEPR chart. How many electron domains does this have? Be careful with your answer. Does a double bond count as 1 electron domain or as 2?
1.
How many voted counts as 1? The camera's not pointing at you, so you can do this completely anonymously. How many voted counts as 2? Okay, the correct answer is 1. And the reason why is because they're being shared between the same 2 atoms. Okay? I always use the analogy, I had twins. I had a twin pregnancy. So that counted as 1 pregnancy, right? Even though I had 2 babies at the same time, that was still 1 pregnancy, right? So if you've got 2 pairs, even though it's 2 pairs occurring at the same time, it's between the same 2 atoms, right? So that counts as 1 domain. So this is 1 domain, this is 1 domain. So the number of electron domains here is 2, okay? So I'll just write it above. The electron domain geometry is linear. And the molecular geometry, are there any lone pairs on the central atom? No. And you couldn't have that scenario anyway, because if you had a lone pair plus 2 domains, that would kick you here immediately, right? So by default, the answer here is also linear. Now let's ask ourselves about the polarity. Is this a polar molecule or not? If you do your calculation of bond polarity and you look up the electronegativity of carbon, which is 2.4, I believe, and you look it up for oxygen, which is 3.5, I believe, that comes out to be 1.1, 1.2, depending on what value you use for carbon. That puts you in the polar range. However, if this is a polar bond, and this is a polar bond of the exact same magnitude, think like your physics people, right? Do these 2 vectors offset each other, so to say?
Yeah.
Yes, they do. So if this one offsets this one, could this be a polar molecule? No. So this is a non-polar molecule. Even though it contains polar bonds, the carbon-oxygen bond is polar. However, there is another carbon-oxygen bond exactly the same that offsets it. Therefore, the molecule as a whole is non-polar. Does this make sense? Yes? Yes. How do we feel about that?
A lot better.
Feeling a lot better? That's good. That's good. All right, so really quickly, because I think we've got enough time to do this. 10 minutes, I think we can squeeze it in. Because our class, we've got 8 minutes. My clock's slow. That's a bummer. I don't like having a slow clock. Because I always think I've got more time than I have. We'll just quickly talk about our intermolecular forces. Intermolecular forces are forces of attraction in between, and that's the key word. In between. intermolecular forces, not intramolecular. Intramolecular forces occur within the same molecule, right? Those are bonds. Intramolecular forces are bonds. That's what holds a molecule together. Intermolecular forces occur in between molecules. So think about magnets. Magnets are the best example. If I go grab magnets off my refrigerator, right, and I put them together, they stick to each other, right? Is that a chemical bond? Is there a transfer of electrons or a sharing of electrons? No, that's a positive and a negative just clicking together, right? Intermolecular forces can be thought of exactly the same way. It's like a positive and a negative interacting with each other. And so the IMFs that you're interested in are London dispersion forces. And this occurs in all atoms, all molecules, and it also occurs, is the only IMF in nonpolar molecules. So I'll introduce this today, and if you still have questions, we can talk about it a little bit more on Friday. Then there's dipole-dipole. And this occurs in polar molecules. And then there is hydrogen bonding. Now don't let that name confuse you. I know the name has the word bonding in it, but it's not a chemical bond. Okay, bonding involves a transfer of electrons or a sharing of electrons. This is not a chemical bond. It's not a covalent bond. And it occurs when molecules contain HF, H, that's an O, or H, N bonds. And then there is ion dipole, which I know we won't get to today. We can talk about on Friday at the beginning. And this is between an ion and a polar molecule. And I'll do an example of this on Friday in lecture. But we can go back to our 4 Lewis structures that we've drawn today and quickly diagnose their IMFs. So let's look at our 4 Lewis structures we did today. CH4, this one's nonpolar. So the only intermolecular force it can have is what? London dispersion. Then we did water. Now every molecule has London, so you can always put that as one of your answers. And then you just ask yourself, is there anything in addition to that? There is. What is it?
Hydrogen bond.
Hydrogen bonding, right.
So what, is dipole one or?
No, because dipole, hydrogen bonding is a special type of dipole-dipole. Now I'll show you an example of one that contains both. But because the only bonds here are OH, that's why it's hydrogen bonding and not hydrogen and dipole-dipole. I'll show you an example of one that contains both on Friday. I don't think I'll have time to show it to you today. Then we did ammonia. What does it have? It has H bonding. Does it have anything else? Right, it also has London. Some textbooks you'll see it listed as just dispersion. Some books will call it just London. Some books will call it London dispersion. I don't want to write all that out, so I just call it London, because that's a shorter word. And then the last one we did was CO2. It was nonpolar. So what's the only one it can have? London only. I've got enough time to sketch it out real quick. Here's an example of a molecule that contains both dipole-dipole and hydrogen bonding. I'm going to have to lose some of my rules here. If you missed it, you can go and look at the lecture, and you can look at the video later on this afternoon. A molecule like this would have all of the above. When you take organic chem or elementary organic chem, which I offer next semester. We can get into this even further. You can break this molecule down. This one's got all of the above. So this region right here is nonpolar region. So it would be the London forces. I mean, the whole molecule's got London forces, but this is London only. Make a note to yourself. Anytime you see a C double bond O, that special region of the molecule is capable of dipole-dipole. Because this is a partial negative and this is a partial positive. And then what does this piece have right here?
Hydrogen.
Hydrogen bonding, right? So this is an example of a molecule that would have all three. And so on Friday, we'll come back and revisit this, and we'll look at how this affects solute and solvent, because I think that was part of what someone was asking about too. And then we'll finish the rest of our list on Friday as well. Tomorrow we'll have lab. So if you have not already purchased goggles, let me stop recording here. You can buy those at the bookstore. Stop. And